as John so eloquently stated, I am involved with the Alumni Association. I've got the great pleasure of leading the organization and working with faculty members like Professor Delaney and others to really bring the rich academic prowess of the university out to our alumni audience and to our friends and to our community at large. This is a special year for the UW Alumni Association. This is the 125th anniversary. And back in 1889, 50 or 60 alums gathered, and they knew that the fellowship and the support and the advocacy for this university would be needed for its success in an early stage, and certainly it's as relevant today as it was then. This lecture series, the fifth of five, the final lecture of Professor Delaney's work with the Undersea Observatories Initiative, is really, I think, an amazing example of what happens at the University of Washington. His leadership over this many decades in this work is extraordinary. Professor Delaney arrived at the university, as you may know, in the 1970s, 1977. He holds the Jerome, Paros, Endowed Professorship in Oceanography. And his work is so much larger than what so many people understand. And the opportunity for you to witness this, to engage with Professor Delaney, to really absorb the fact that groundbreaking science and transformative exploration occurs in his program and here at the university is really extraordinary. So on behalf of the Alumni Association and our many, many efforts to really bring the exciting work taking place in the university to you and to our larger audience, thank you for coming out on such a cold, crisp evening. It's great to see you here. So Professor Delaney, they know you well, and I know that we're scheduled to end, I think it's 9:30 tonight? Maybe a little bit earlier. Please join me in welcoming Professor John Delaney.
God, I don't know what to say to you. We had an unbelievable summer. It was, I and a number of other folks were at sea on the Thomas G. Thompson University of Washington research vessel for 84 days offshore. And my colleague Deborah Kelly is here somewhere. She was co-chief scientist on it. There she is, back in the back next to Orest Kauka, who is also at sea. There are a number of these folks are in the audience. And it was an unbelievable effort by a remarkable team of folks from the Applied Physics Lab and from Oceanography here on campus, and our colleagues at Oregon State, where they also have a major part of this program to change the way, to usher in a transformation of the way in which oceanographers study the ocean. And that's part and parcel of what we're talking about. So what I thought I would do is, since I think some of you, I can't believe as many of you came back, since I have abused every time you've come, I've abused you by holding you here more than I think I'm supposed to talk for 47.6 minutes, and then there's supposed to be 11.2 minutes worth of questions, and then we're all supposed to adjourn, and then the fire marshal comes through and wakes everybody else up. So, but I've never stuck to that, and I'll try tonight. So I believe surely you'll be home, as I said in earlier lectures. I'll try hard to get you home before midnight. What I'd like to do very quickly is go through some of the key elements of the previous lectures so that you have a sense of the whole setting, the whole effort here. And I have been very candid with you that I was pushing the envelope myself when I decided to address something like the global ocean and human culture. I mean, who in the world, past, present, and future, who in the world could do that? But I thought it would be fun to give it a try, and I have invited significant feedback from any of you. My name is J. Delaney at uw.edu. I welcome all sorts of feedback, but I would remind you that compliments are nice, but good criticism is the one way that you can improve, and that's what I'd like to be able to do. So please give me your feedback if you feel up to it. So this is on April 15th. There was a lecture, and these are all now being aired by UW-TV, the first four. So the first one was Human Culture, Science of the Ocean, Art of the Sea. And one of the things I wanted to talk about there was how ancient cultures, back 5,000, 10,000 years, moved across the ocean, and the Polynesian societies have an unbelievable record of moving across the ocean as if it were Main Street, and they would go thousands of miles from island to island, and they had populated the Pacific in easily 1,000+ years ago. And in fact, people had crossed large tracts of water to get to Australia as much as 50,000 years ago. So traveling across the ocean is an integral part of human culture and has been a key part of human culture for a long time. In fact, many of you perhaps come from Europe, and I would be willing to bet, since these are the patterns that the voyages the Vikings took, even if you've never been to Scandinavia, I wouldn't be surprised if there's a trace of Viking blood in each of you, because some of those gentlemen did not behave very well as they traveled around Europe, and they certainly did travel around Europe. The other thing is the ocean has always been a place of danger, a place where people were afraid. And at the edge of many of the maps, it would say, "Here be dragons," or "Here be monsters." And Alfred Lord Tennyson picked up on this, and I love this little poem of his, The Kraken. Everyone, no doubt, has heard about the Kraken. You may now know that Edie Witter, a colleague from Florida, actually used electronic bait to get the first pictures of a giant squid, which is as close to the Kraken, I suppose, as we'll ever get in real life. But this is what people thought back in 1830, when there were actually dragons at the edge of maps. Below the thunders of the upper deep, far, far beneath the abysmal sea, his ancient dreamless uninvaded sleep, the Kraken sleepeth. Faintest sunlights flee about his shadowy size. Above him swell huge sponges of millennial growth and height. And far away into the sickly light, from many a wondrous grot and secret cell, unnumbered and enormous polypi winnow, that with giant fins the slumbering green, where hath he lain for ages, and will lie, battening down huge sea worms in his sleep, until the latter fire shall heat the deep. Then once by men and angels to be seen, in roaring he shall rise, and on the surface die. I think Tennyson sold a lot of those poems, so it's really quite interesting that the figure that I use here is actually taken from one of the illustrations of the very famous novel by Jules Verne, 20,000 Leagues Under the Sea. So you can see that the Kraken caught the imagination. Now, on the other side of the coin, the ocean has often been the stimulus or the element behind the creation of unbelievable beauty. Let's see what it looks like. Not only that, Winslow Homer imagined what it would be like to be desolate in an open boat with a broken mast in a place called the Gulf Stream. And the Gulf Stream is a very, very powerful flow of water that moves through the Straits of Florida and takes an immense amount of heat from the Gulf up into the northern latitudes, and has modulated the conditions in northern Europe for the last 10,000 years. So this is the poetic, or the artistic side of that, and this is the historical side of that. A gentleman by the name of Benjamin Franklin actually mapped out the Gulf Stream by looking at the arrival times of ships coming to America and from America. And he found that the ones that were going toward Europe, actually, the trip was about as much as a week faster. And he wondered why. And before long, he was able to figure out that such a river in the ocean existed. There are many other aspects of this, but I find these things fascinating. I find human culture and the way it relates to the ocean is very, very diverse, very, very captivating, and there's a great richness. Now, if I could slip seamlessly into science, the kinds of biology, the kinds of organisms that live in the ocean are just exquisite. I mean, these could be pieces of art. They happen to be pieces of life. Silica, the outer surface of this creature, it's wrapped, every one of them is individually wrapped in silica. They're dined upon by Euphausia superba, which is Antarctic krill, which, by the way, is bioluminescent, in case you've never noticed. You may not have had the opportunity to catch that, but they are bioluminescent, as are many creatures of the deep ocean. And there are additional creatures of the deep ocean that you probably dine on from time to time, and you're not alone. You're not alone. There are predators that are actually dangerous even to us, but they are also beautiful. They're also magnificent. And all of these are of the ocean. There's also the interesting environment that we live in. You can all identify Kane Hall, which is over there on Puget Sound. Which room is this? 302? So we're in 302. But what does this look like? We have a subduction zone where the Juan de Fuca tectonic plate is plunging beneath North America, creating the Cascades, and on occasion making an awful lot of noise in the form of a magnitude 9 earthquake. The spreading center offshore, about 300 to 500 kilometers offshore, is actually always pulling apart at about the speed your fingernails grow. And what's the cross-section of this look like? It's kind of cool. I've dramatized this a bit with the graphics by Mark Stormer, but that's kind of what you're living on top of. You see there where it's melting? If you went just a little bit east, near Mount St. Helens or Mount Rainier, you would be above the part that's melting. And over in the middle there, or to the left, is the part that rises at the ridge crest. It's also molten, 1,200 degrees centigrade. It's basalt, similar to the material that comes out of Iceland and Hawaii. And there are unbelievable forms, natural forms. Just watch the transition. Watch it again. And what's the meaning of the almost perfect similarity? I don't know, but it's really beautiful. And then this is one of my favorite quotes by Rachel Carson, who unbelievably said the following: "If there's poetry in my book about the sea, it's not because I deliberately put it there, but because no one could write truthfully about the sea and leave out the poetry." So the boundaries between art and science and human experience are part of the spectrum of human culture. And I think we should be teaching it that way in our universities. I don't believe we need to have this hard, sharp boundary between that which is science and that which is not. Lecture 2, and that was a long, I won't be as lengthy about the others. What paths technology, science, oceans, and humans? Very briefly, we need to be thinking about what we are doing, what we are leaving behind. Many, many of these albatross carcasses are shown to have all sorts of plastics in them. And there's a long and deep and complex and sad story about plastics in the ocean. And there are many ways you can read stories about it. I simply mentioned to you that some of our successes are not necessarily successes for all folks. Then there's the powerful part of what kinds of questions do we ask? What are the origins of life on Earth? Where did they come from? And, you know, it's a question that Deb Kelly and her colleagues have been working on, is what are the limits to life? Do we know? Do we really know? She's found some evidence that life inside some of these hydrothermal systems on the sea floor, this is a vent at 1,500 meters water depth, a kilometer and a half, that looks like they're candles, but actually it's boiling. It's at 340 degrees centigrade, and it's on the boiling curve. So those are actually tiny little bubbles that, as they flow out, mix with cold seawater and they're quenched, so the bubbles disappear. But the light's shining off the refractive surfaces of the bubbles. Many, many facets that we are curious about. And if you lived in Coos Bay not long ago, you see that arm that goes across there toward Coos Bay, toward North America. That one created some harm. Well, this is the 2011 Tohoku earthquake tsunami, and that's kind of where the concentrated energies are. So it's a very complicated phenomenon, and we're beginning to understand it, but we don't have any way right now of controlling it. We just hope to understand it and then be smart. And as you well know, the United States is one of the dominant players in naval engagements. In fact, you could say that the ocean is the basis for a huge amount of transportation for goods and services. It's also the concentration of places where force projection is most effectively done by the nation that can, in fact, dominate the ocean. And since the end of the Second World War, the development of a nuclear sub-fleet pushed for 30, 40, 50 years, pushed oceanography forward rather aggressively because the Navy wanted to know as much as they could possibly know about the ocean, because that was where these types of vehicles and those that you read about in the Hunt for Red October were actually vying with each other in the dark. And our own setup, where are we? We are on the head wall, so to speak, of the Cascadia subduction zone. It's a geologic setting that has megathrust earthquakes. And if you look carefully at this diagram, again, you can see where Kane Hall is. You can also see that the arrow coming from just above the F in Juan de Fuca is coming, the plate is coming ashore at about 43 millimeters a year, 4.3 centimeters a year. And it's doing that and doing that and doing that. And it's fairly quiet, turns out, until it's not quiet. And about 314 years ago, there was a major earthquake in this area that created an orphan tsunami in Japan, but was eventually, as a result of unbelievably good research by a number of folks, created the indication that it came from these shores. So we think that that was the last major earthquake. The recurrence interval, as far as we know, for that type of activity is roughly 300 to 500 years. So it's worth being aware that sooner or later we will have to answer the question in Cascadia of when. So the Tohoku earthquake in 2011, the Chilean earthquake in 2010, and the northern Sumatra earthquake in 2004. The question is, when? And what happens is that reddish zone in the inset, that's locked for reasons we don't fully understand. It gets locked and then becomes unlocked. And when it becomes unlocked, Vancouver Island stops rising because it's being pushed up by the subduction. It's this type of thing. And when it slips, Vancouver Island will sink quickly, and a lot of the rest of the area will react in one form or another. Magnitude 9 earthquakes routinely cause tens of billions of dollars of damage and sometimes more. Here's something I love. These are connected to a fiber optic cable. This is Imagineering. This doesn't exist yet. The yellow robots have 14 sensors on them, The orange ones are the navigation balls. They tell you where the cluster is. The green ones are the communication balls. And it's in the search mode. Marcel Proust has produced this unbelievably good note that the real voyage of discovery consists not so much in seeking new landscapes, but in having new eyes. And I think he was speaking metaphorically, but you can take it metaphorically or literally. It really captures some really basic views, and we'll talk a little more about a set of new eyes that currently exists on the seafloor right now. And finally, Greg Sattel said, we need to fundamentally change the way we think about talent, putting less emphasis on predetermined sets of skills because of the rate of change of both technology and society, and more focus on the ability to acquire new ones. This is not suggesting that we abandon basic training in science, but it is saying that in a rapidly changing world, an entrepreneurial spirit is the one that will serve you best. And that perhaps is worth thinking about. Volcanoes in life, I have just a few points to make on that. There's a lot of material out there on it, and there is, this lecture is actually there. I wanted to show you the three gentlemen that are responsible for discovering submarine hydrothermal systems. On the left is Jack Diamond, and Jack Corliss in the middle, and John Edmund. Discovery that happened in '77 and then again in '79, they actually saw black smokers. And this is a compilation that Deb Kelly did that shows that there's at least 300 of these kinds of systems around the world. And that's just a limited effort. There's a lot more than that, but those are the ones that have been discovered. This is an example of what's down there. And this is a quick commentary that instead of photosynthesis, which we're all used to, chemosynthesis is the use of energy released by inorganic chemical reactions to produce food. Chemosynthesis is at the heart of deep sea communities like the one I just showed you. Sustaining life in, it's not quite absolute darkness. They all photosynthesize, or they all create bioluminescence in one form or another, where sunlight does not penetrate. Now, I wanted to share this with you just for the laugh. About 15, 16 years ago, a couple of us decided that we would go and find one of these big black smokers. We would harness it. We would use, from the Pacific Northwest, we all had red suspenders. We went out and used a chainsaw. This is in 2,200 meters of water. And we wanted to remove one of these so we could see what lives inside. And this is the way it was dressed up before we began pulling on it.
At the load we're at right now, if it was a free hanging rock down there, it'd be too heavy to bring aboard. We'd go over the 30,000 pound type of thing. And I think it just broke.
It came loose and it's coming up. You're the luckiest bastard.
Rowan has broken free from the seafloor. One hurdle is passed, but what lies ahead will not be simple. They appear to have a multi-ton chimney on their line, and no one knows how difficult it will be to handle.
Here it comes. Here it comes.
Here it is in sight, right at the surface.
We got multiple pieces. Look at the smoke coming out. Okay, steady it up.
At the surface, two huge pieces of Rowan hang from what seems a fragile thread.
I would think we might be better
to get on the wire?
I wouldn't get on that one because you may pull it off.
One slip, and this precious haul could plunge back to the depths.
Okay, let's get the next one and steady into the top here.
And that's not all that could go wrong.
Okay.
You want to do the same thing on the other side?
My greatest fear is hurting somebody or killing somebody, and it's a very strong potential that you get this rock swinging on the deck.
Okay, just play it easy there.
You can think of a wrecking ball, and you're trying to control it and get it onto the ship and secure it down.
Now they must handle two swinging rocks at once.
Okay.
That's incredible.
Even after traveling through 1.5 miles of ocean water, Rowan is steaming at nearly 200 degrees Fahrenheit. Its surface is covered with tube worms, some still alive. Its interior is filled with billions of microbes.
We will have more samples, better collected samples, and better analyzed samples from these structures than we've ever had before. That has, for me, the same kind of fascination and sense of discovery and exploration that I would have if I got to go to Mars and drill, let's say, a kilometer down into the regolith and look for water and life there. I have the same kind of excitement that I'm going to find something really different and something that's going to be, you know, a profound importance in understanding how life originated and how life evolved.
That's part of the prelude. This is, I'll be very short on this one, but visually give you a sense. These are the topics that we discussed in the 4th lecture. I'm sure all of you remember all the details, but in fact, that we did touch on every single one of these. John Barros and I sat right there, same John Barros you just met, and we worked our way through these, and it was very gratifying to me to do that with John, and the questions that came out of this audience were unbelievably excellent questions. I was just so pleased at the kinds of questions, some of which we didn't answer very well. But we tried, and there's a huge amount of material out there. Once you get off the planet, or once you go way back in time, it's a pretty fascinating place, pretty fascinating. So some of what we're doing at the cutting edge underwater may well be at the cutting edge underwater on other planets when the time is right. All right, so there we are. Those are the 4 lectures, and this one sounds a little bit like what I did with my summer vacation, but I'm afraid to some extent it is. And what I wanted to do is give you a little bit of background of what we've done. We have spent $150 million of your tax dollars in order to change the way oceanography is being conducted offshore and hopefully around the world within a decade or two. So here is the way we started. You can see what Neptune, the cabled system, used to look like. Every one of those was a single node with 20 to 50 instruments around it when we were in our original plan. And that's the shape of the Juan de Fuca tectonic plate. So that was the view in 2001. One of the reviews I got from one of my proposals early in my career was, this thing by Delaney is what was this? The worst case of unmitigated hubris I have ever encountered in a scientific proposal. So there you are. I think it was just a conservative gentleman. So this is what the National Science Foundation launched in 2009. The University of Washington signed for something in excess of $200 million to build the system that I will share with you now. And the sites in the southern hemisphere are the 2 circles. In the northern hemisphere, there are 2 circles. Those are all satellite-linked moorings with what are called gliders, which are porpoising autonomous underwater vehicles that can move about under control from an iridium, that is a communications satellite with a telephone link to these things when they come to the surface, so you can tell it what to do next. They don't have much of a payload. They don't move very fast, but they work, and they work extraordinarily well. So Erminger C, Station Papa, and the 2 sites in the southern hemisphere are occupied, will be occupied within 6 to 9 months by these kinds of facilities as part of the Ocean Observatory initiative. The Pioneer array on the East Coast is similar to those, satellite-linked moorings and gliders, and an autonomous underwater vehicle. But the box on the left coast is the one that we know the most about here. We are teamed with the folks from Oregon State and the Endurance Array and the regional scale nodes, which is what the NSF Marketing Bureau didn't like the word Neptune because it smacked too much of the University of Washington, and they wanted this to be a national facility. So their marketing group came up with regional scale nodes as a replacement for Neptune. Neptune stood for Northeast Pacific Time Series Undersea Networked Experiments. RSN stands for Regional Scale Nodes. I don't know how much you know about the physiology of the early stages of Black Death, but look under that for scaly nodes, and you'll understand the marketing side of this whole thing. Surely some of you can help. In any case, we forged ahead with a label, and here is what we have. That expansion of the box is what you see there, and here is what is in existence right this minute. The Canadians to the north have put in, about 6 years ago, put in a loop-like topology with about 6 nodes on it. Some of them in shallow water, 1 or 2 in deep water, and 1 near a drill hole in the seafloor, an array of drill holes. The southern part there is what was put in by the Ocean Observatory Initiative, OOI is the term used, and it's the Cable Ocean Sensing Network, my term. And you'll see over by the shore, there is 1 cable that comes down to the deep blue ocean floor and then goes back up toward the shoreline, called the Endurance Line or the Hydrate Ridge or Slope Base. Remember those words, Slope Base, Hydrate Ridge, Endurance. And then off all the way across the plate, right past mid-plate, which is not occupied with any heavy-duty electronics right now, is Axial Base and Axial Caldera. Axial is an active underwater volcano. It is the most active volcano on the Juan de Fuca Ridge, which is about a 500-kilometer long seafloor spreading center, similar to what goes through Iceland, and it's a 70,000-kilometer ridge crest. And we have about 32 instruments on top of that axial caldera right this minute. We'll come back to that. Here's another look at it. The orange lines are fiber optic cables that were laid by a big ship. And let's talk about it. That's part of the primary infrastructure. What you're looking at in the background there is a node. We'll come back to the node. But in order to get the cable ashore, we had to drill from behind the dunes down in Pacific City. I'll take you back to show you where Pacific City is. You see over by Portland. Pacific City is right on the coast. And here we are at Pacific City. The Nestucca Bay is right there. And the shore station is exactly where you see it, the green box. And about not quite a kilometer south is the set of drill holes that drill down underneath the seafloor and come up about a mile offshore in water depths of about 20 meters. It's like a tunnel for a cable. That's right. And then the cable ship came in and laid out cable on the surface of the water, and it was pulled with a rope that was pulled through its cable onto shore and then connected to the shore station. All right. That all happened in 2011. And the cable, they're both the red line, the green line, sounds like the metro in DC, were laid at that time. It's about 900 kilometers of cable. It was all laid using that same ship, the Dependable. CS means Cable Ship Dependable. It's just the right name you want for a ship that you depend on. And then primary node installations, you see two graphics of them on the left, one with doors on it and one with doors off of it. The one with doors on it is supposed to shed, and the fishermen come along and catch hold of it by accident, we hope. That form will shed the fishing gear. The deep water configuration is below the depth that fishermen fish, and so we don't have to put the cost of the armor or the cladding on top. But July and August 2012 is when all of these things were put in place. Cable in 2011, July, August 2012, and this was overseen by folks like Cecile Durand and Brian Ittig. I'll show you pictures of them here in a bit. And this is what it looks like. That's the shallow one, trawl-resistant frame, and it has basically two backbone cables that allow it to distribute 10 kilovolts of power and 10 gigabits per second of bandwidth. And this is one being launched off the fantail of that giant ship that you just saw. It's in the air. It's very heavy. And there it is on the seafloor. And it was immediately wired up. And this has been in place for some time. Here's the operation that it takes to wire it up. You'll see an arm of an ROV reach in and grab the cable. The other arm is holding it, see on the left with the color bands. And it's plugged in. Oh, and there's the local neighborhood is pretty crowded, actually. And you'll see an octopus here very shortly. Looks like he's stretching after a nap. It, I don't know. I've always found it difficult to sex an octopus. Is there anyone? Later. But that's the way the plug-in goes, and everything is kept detailed records of everything that is done. And some of the students that are here in the audience can talk to you afterwards if you come down. I'm sure they'll come down and chat with you about what it takes to record all the information that they were very, very unbelievably valuable and helpful in doing this summer. So this is what it looked like early 2013. 2 cables, 1 landing, 1 cable station, 2 scientific sites, that is near the coastal subduction zone over here by the edge of the continent, and the other one offshore at the spreading center across the Juan de Fuca tectonic plate. These are the 2 gentlemen who man the shore station all year around the clock, keeping track of everything that goes well and also solving all the problems of what doesn't go well. The secondary infrastructure, I just described the primary infrastructure to you. The secondary infrastructure was put in by this vessel, which is only 273 feet long, but the University of Washington operates it. It's called the Thomas G. Thompson. And all of the secondary infrastructure was put in by the RSN team from this ship, 48 days worth in 2013 and 83 days of 2014. And the remotely operated vehicle that we used is called Ropos. On the right-hand side, you can see the name. And that is a vehicle that is on a cable. It is, we call it ROV, remotely operated vehicle. Underneath it, in the right-hand side, is the green and cream-colored body, which is actually what we call a secondary node. And it has a switching box inside it that allows us to take the high power and high bandwidth from those primary nodes and step it down to something that the instruments can use, or to daisy chain it out across the sea floor. On the left is what we call Rockles, a remotely operated cable laying system. The same ROV on top, but underneath is a reel, and we take the reel on the sea floor, we anchor it in one place, and we begin to pull it. And it's just like hooking a fishing line somewhere and then walking across a field. You leave behind line behind you because you're walking away. Why you would do that, I don't know, to get away from the fish or the stream. But in our case, we lay these cables ourselves between the big cables that were laid by the big ship. So this allows us to have neighborhoods. It's like in your neighborhood, unless you live in special places, you probably have power and telephone poles. Well, the power pole is the one with the cross arms up on top, and it sometimes has a transformer on it. And if you were to follow those power lines somewhere in your neighborhood or beyond your neighborhood, it would go to a major substation where the power switching is. That's what those primary nodes are. That's the switching station for the big power. But the transformers in your neighborhood are the equivalent of these little green boxes, not so little. So this is what it looked like inside the cave of control on board the ship, where we operate the entire ROV, and in front of the scientists, you can see their backs of their heads, are a group of skilled professionals who operate it all the time. And there's something, I can't remember, but it's something like 20 flat screen TVs give you continuous access to whatever is happening in the place. And the students and the scientists who are operating and in charge sit behind them, and they record every single thing that happens in great detail. And we have all those records. If any of you would like to read those records, some of them, it's about, I would say, a dictionary worth. And I can have those sent to you personally in your office if you like. It's just fascinating reading. Don't you think, Max? Lauren? Taylor? Jeez, when did you get in? Junction boxes. That's what they look like from above. You can see the silver thing inside. Let me change it. The silver thing inside is where the electronics is. That's the brains of the whole thing. And from land, 400 kilometers away, people can, here on campus, we communicate with these things, and then they communicate with the instruments that are attached to them, and we tell the instruments to turn on. We send them power, they turn on. We tell them to make measurements, they make measurements. We tell them to send data, they send data. It comes all the way through the shore station, through Portland, and up to Seattle on campus here, and that's going on right now. We've done that this summer. It's working. We delivered on time and on budget a program that will allow you and your family and your grandchildren and your children to tap into what's going on underwater on a routine basis. Now, it's not quite ready, but I'm going to show you what some of it looks like. Now, for those of you that are engineers, beyond redemption, I wanted to at least show you what the functional block diagrams look like. And every one of those nodes I just showed you, that unit, is represented by one of these boxes, and it's connected to a primary node. You can see across the top are primary nodes, and a network of these secondary nodes, low voltage, low power, they're all connected. And so there's this network, and you'll see more of that later. This particular one was deployed at the base of axial seamount, and we'll talk more about that in just a bit. And it's connected by cables, and the cables are laid by the rockles on the bottom of the ROV. And what you see are cables that are about this. Here's one about to be launched and laid. It looks like it's only got about a kilometer of cable on it. We laid cables up to almost 5 kilometers long, and it took a long time to do this, a long time. Here's one of the biggest ones. It had to be put down. The rope post wasn't strong enough, so we had to lower this on a wire from the ship itself, and it's just touching down. And here's the primary node, and here's a secondary node, and these are connected to one another, but they're not side by side shown. The secondary node would be off over by the tower, and another secondary node would be down by Oceanography, and a third would be University Village, and we'd be able to talk to each of those, and then operate all the instruments that are in that neighborhood. So this is the ship, or the red boxes are the primary nodes, and we went to sea with a fascinating capability of communicating ashore using satellite link, the Galaxy, which has a gigantic footprint, and we were able to communicate at about 5 megabits per second coming ashore, and back out 3 megabits per second. So we were able to carry on dialogue. We sent live streaming HD video ashore on a routine basis all summer long. And it was distributed across the country, actually. And here's a sort of a potpourri of impressions that you would have if you'd been at sea. The lady in the upper left has what we call a Gumby suit. It's a survival suit. All the people that go to sea have to prove they can get in and out of a Gumby suit in less than a few minutes. And the all-time winner of that is sitting right back here. Mitch, could you stand up? Mitch Ayland is capable of putting one of those things on. He's capable of putting one of those things on in 8 seconds flat. It's unbelievable. It's unbelievable. So there are many, many aspects to this. The dolphins were not with us the entire time, but they came by every now and then to chat. Different meetings. That was a big storm in the middle there. Here's all underwater shots, again, a potpourri of what we imaged and encountered. Here are some of the students from Visions 13 last year, and they are still near and dear to my heart. These were unbelievably hardworking, just joyful folks to be at sea with. Here's this year, Leg 1 students. A couple of them are here. Could those of you that are students that were at sea with us, would you mind standing up just for a moment? And murmur, just murmur. Yeah. Why are you so far back? I don't believe it. So the lady on the far left, and the gentleman next to her, and the gentleman next to him in the blue checkered shirt, were the 3 people that were involved in producing this video. They produced this video at sea. They did it. Faculty was there to encourage. Oh, and on the far right, 1 point in, is Deb Kelly, my colleague Deb Kelly, who I've been working with for 30 years. She was 6 when we started. And all, I mean, the rest, Charles is here. Charles is the guy in the purple shirt, of course, you know, UW, that type of stuff. Anyway, so here's what Katie and Sam and Jesse put together.
Our oceans provide us with over half of the oxygen we need to survive. They have absorbed greater than 40% of all our carbon emissions and contain more heat in the upper 2 meters than exists in the entire atmosphere. To say that we depend on the oceans would be a great understatement. And yet, their complexity still mystifies the scientific world, and we have created better maps of other planets than we have of the seafloor. Current methods of collecting ocean data are often sporadic, lasting only weeks or months at a time, limited by the constraints of research vessels and the battery life of deployed instruments. Bad weather can bring all scientific pursuits to a halt, and necessities of fuel, food, and supplies prevent year-round data collection from ships. But all of that is about to change. 300 miles west of Oregon, deep beneath the sea surface, a network of cabled observatories is being installed on the largest underwater volcano off the coast, called Axial Seamount. This project is part of the Ocean Observatories initiative and is creating novel ways to examine the oceans and interact with some of the most extreme environments on Earth. The instrumentation has been custom designed to withstand near freezing temperatures, endure pressures 150 times that on land, and tolerate an entire ocean of corrosive salt water, all in the absence of light. Armed with these resilient tools, we can have an unprecedented view into the mysteries of the deep. We will have a presence in the ocean at all times, measuring every variable we can. Instruments will be able to detect a rise in the height of the volcano to the accuracy of a millimeter. Every earthquake trembling deep beneath the ocean will be known about on land at the speed of light, with seismometers that can pick up even the faintest of vibrations due to their proximity to tectonic plate boundaries. There will be motorized vehicles climbing cables that reach all the way from the ocean bottom to the sea surface, measuring the distribution of organisms, fluctuations in ocean acidity, and changes in dissolved oxygen every minute of every day. And with a fiber optic cable running over 300 miles to shore, this network will generate a non-stop flow of real-time information, streaming directly from the oceans to people around the globe. Year-round, 24/7 collection of data, soon to be available from anywhere with an internet connection. This development has been made possible from the funding provided by tax dollars allocated to the project by the National Science Foundation, along with the invaluable support of numerous organizations. This communal tool will be used to create a shared consciousness within the ocean. With your help, we will soon be able to tell the stories of the deep as never heard before, and feel the heartbeat of the volcano as if we were there ourselves. Come to our website and bring your ideas, your knowledge, and your interest in order to better understand Earth's most vital life support system.
Isn't that something? And that's only one. I mean, every single student in our student group out there produced something comparable. It's just so gratifying to see what these young folks do. And that was done on their own. I mean, we provided the framework and some of the content, but they chose the final, all the decisions of what to do and the final decisions as to what to show and the music to use and the language to use and the discussions was all from people that are less than 21 years old. It's really cool. These are the Leg 2 students. The narrator is Jesse in the gray shirt. Sam is just his left behind him in the blue shirt. One of the recurring students is the one next to me, the tall lady with blonde hair, and Caitlin Russell. And off to the far right, your far right, is Brendan Phillip, who's been out with us 3 times. This is leg 3. At least 2 of the leg 3 folks are here. And I hope they'll come down afterwards and chat with any of you that are interested. Leg 4, I see Taylor over here. Certainly Lauren is here. All of you, please come down. So these are the folks. This is given to me by Lauren today. These are the folks who have worked on what we call now something different, a deep sea biology catalog in video format. And I'll just read their description. These are produced by the students. Without reading an entire scientific paper, it's difficult to find more about many deep sea organisms than simply a picture and a name, especially those surrounding hydrothermal vents. Our biology catalog is meant to be a bridge between those 2 extremes, allowing people outside the scientific community to better understand and appreciate the incredible environment without inundating them with overly scientific jargon. It was also created in the hope that it can be used for general educational purposes so that people around the world can read about and watch the biology of the deep in their natural habitat of the biology, not the natural habitat of the people who are watching. But the whole point behind it is with a cable and mobile platforms and cameras that can be panned and tilted and zoomed, you'll see things like this, a cockatoo squid. Now, I want you to watch this really closely. You will be astonished. See how red it is? It's pretty red. Now watch. Talk about a perfect organ donor. You know exactly what you're getting. It's not clear to me how this is a defense mechanism, but then I don't understand the world very well down there. But isn't that amazing? The students have done research into its behavior and life cycle and are posting these things on the web so people can get access to them. These are babysitter snails. Wait till you see these high-rise dudes. They lay the vertical egg-cased towers, and you can see some of them at work, and others have either fallen off or been eaten by crabs or whatever. But notice something. I mean, I'm a geologist, right? So what I see is rocks, because every single one of these has a rock firmament that it is attached to. None of them do this on sand. The third, I probably will have one of the students talk about this. Paros is a rare little dude. It hasn't been seen, actually. What I think it was 1950s is the last time it was seen. 70s. What year? What day? What month? That was Lauren, right? Anyway, so I don't know. Guys, how many of these clips are there now at this point? A lot.
More than 36.
You know, primitive tribes used to count 1, 2, many. Is it more than many? So this is one of the students working with Oris Kauka, who's in the audience. And this is Brendan Phillip looking at his bubble plumes. Sensors. What did we put out as sensors? Well, this thing that looks like a kid's Tinker Toy set was put together by Giora Proskrowski, and it is something like 31 different temperature sensing devices in an array, so you can measure the change in temperature very close together. Now, all the instruments, and I'm not going to bore you with every bit of information here, but some of you are perhaps more directly interested in the specifics than others, and we can certainly make all of this. This is all on the website. You can get to it. But we put out more than 100 instruments this summer. We'll be looking at geophysical, geological, chemical, biological processes throughout the ocean. And then the cross-section in the upper right is from the deep ocean. The blue part is the 2,900 meter water depth, and the shallow red part is right up near the continental shelf, about 200 meters. And these are the instruments. Now, you're not going to recognize all of them, but take your time and look at a few, and all of that data is going to be streaming all of the time ashore and available to all of the people. You may just watch the video, but you could also look at what's going on in terms of ocean acidification, because we will have those sensors out there as well. A seismometer, a short period seismometer. This is what you saw, the ROV was turning, the upper right-hand corner was turning a little screw that allows us to level it up, and you can see the spirit level in the middle there with the white ring and the yellow interior. That black ball is perfectly centered, so this thing is completely horizontal, and we are already receiving data from this particular unit. These are all seafloor instruments, and there is a profiler that is moving up, breaking the surface of the water and coming back down in about 80 meters of water. The moorings, this is an unbelievable success story. The moorings that look like these two, the two-legged one goes up, two legs all the way up to about 200 meters below the sea surface. And then there's a profiler that starts there and goes up almost to the sea surface, and then comes back down under control from land all the time. And on the left-hand side is a single mooring called the deep profiler, and that's the package that climbs up and climbs back down, climbs up, climbs back down 9 times a day, and sends the data home. So there are instruments on the winch package, there's instruments on the 200-meter platform, there's instruments on the profiler, and there are instruments on the seafloor. Here's how the profiler works. The deep one is on the right, the shallow profiler is on the left, and the man that designed the profiler and did all the software is in the room here as well. Eric McRae will certainly be down here afterwards if you'd like to speak to them. These are the locations. You see the tiny little arrows from each of the boxes show the location of both of those things side by side. On the right-hand side is the endurance site. Slope base is the one in the middle, and off on the far left is the one at the base of axial. Remember those names: axial base, slope base, endurance. Here is the profile that you saw before in a distance, and here is what these things look like, and that's exactly where they are. They're located in those sites. This is a perspective drawing done by Mark Stormer and his colleagues at the Center for Environmental Visualization.
How do you keep ships from hitting them?
We keep them below the level of the rotors. We stop the shallow profiler from getting right to the surface. And as time goes on, we will equip it with detection capability. Once we understand it better, we'll have the detection capability to determine whether there are any motors in the area, and we'll be able to come to the surface eventually. But right now, we keep it safe because it costs a lot of money to put it out there. Here's the climbing package. You see it, it climbs that yellow cable that's being deployed right now. Here is the gigantic flotation package, the 200-meter package being put over the side. And here is the flotation package, the 200-meter rise package. And that's Orist on the left and Trina Lichtendorfer on the right, fixing it before it goes into the water. Remember, this is how it works, and they actually work. They're out there, and they're done by the folks at the Applied Physics Lab. Modified one design for the deep profiler and came up with their own design for the shallow profiler, and they put it together and it works. It's amazing. This is what it looks like when we go to sea on the left, and when we come home, we've put everything in the water. And this is what it looks like on the sea floor. This is what we put out. 90 remotely operated vehicle dives all summer long. We put in more than 30,000 meters of extension cables. We put in 17 junction boxes, all of which are working. 140 instruments, 30 different types. Way more than 90, it's about 97% of them are working. 3 state-of-the-art shallow profilers. There is nothing else on the planet like them right now. The deep profilers are a modified version, and we have 2 benthic experiment packages. Now, what's the data look like? Well, here's the flow pattern. Now, this may not mean much to you unless you're an engineer and you know the jargon. So I filled it in a little differently. This is what it looks like as of now, yesterday. And you remember I asked you to remember axial base, slope base, hydrate, endurance. All of the data that's in green is flowing from those places, flowing ashore to the shore station. From shore station to the left, it goes to Portland, and then from Portland, it comes to the UW campus. And then we have ways of interacting with all these. There is what we would call the overall management system, the OMS. The EMS is the secondary infrastructure management system. And then L3, which is the contractor that put the primary infrastructure in, had their own management system. So all of these are part of the system, and we can operate any part of it at any time in any way we choose. And this is what it looks like from the point of view of geophysical instruments. You can look at the drawings. I don't know if you can read all of the print is a bit fine, but in each of these locations, there are a number of geophysical instruments that all of which are sending data ashore as we sit here tonight. Hydrate Ridge. Hydrate Ridge is the one you can see over as it goes back up the shore, up the coast, from the blue water up toward the shore. You can see where it says hydrate. That's that red box. This is hydrate. Now hydrate is a place where gas hydrates have formed ice. Methane mixes with water at certain pressures and temperatures, and it forms a solid. And that forms in this area. Now, there's a pinnacle there. That hummocky topography on the right is where we are with this image. Now, I'm going to show you what comes out of the seafloor in one of these places. This is called Einstein's Grotto. This is an HD video taken while we were at sea this summer, or in previous summers, but also this summer. And you're seeing bubbles, methane bubbles, coming out of the hole because the temperature down there is beginning to change and the gas hydrate, ice, is beginning to volatilize. And the bubbles are released and it comes out. And they erode holes in the sea floor from below, and you'll see that process in just a minute. When there is a major burst, it really knocks a lot of sediment from below the sea floor. On the sides of the rocks, you'll see lots of particulates be right about here. We're going to, right now, you'll see it. See it now, right there. And it turns out with the magic, I can actually take you back. Look at that. Those are all bubbles. Those are, and they're released in pulses. We don't quite understand the pulsing yet, but look at all the particulates, all the fragmental material that's being wafted out by these bursts.
How deep is that coming from those particles?
Terry, that we do not know. It's well below the seafloor, but we don't know. And that's part of why we have seismometers there. We will be tracking the seismometer. So the whole area is configured as an underwater laboratory that will allow us to answer questions just like that. All right, so this is the wired part of this system. That's the hummocky topography there. And up there by MJ01B is where Einstein's Grotto is. And you'll see that we will lay in a camera there. That's the camera put in place by Deb and her colleagues this summer. And there's Einstein's Grotto. And they've already started to take pictures. This one was taken on September 18th, and this one was on September 22nd. Look at the changes. That's microbial growth on the face of the rock. Took place in 4 days. We didn't know that could happen. We haven't been there that much and that often. But we can take a picture there anytime we want. It's about 250 kilometers from Seattle, but by going down to the Ocean Teaching Building, there are people there who can turn these things on, take the pictures, take 20 pictures in less than 5 minutes if they want, or take one every hour or one a day, whatever we decide to do, we have that control from land. And that'll all be made available on the web as soon as we can. Now, just something about methane hydrates. There's a lot of them. Gas hydrates represent well in excess of 10,000 gigatons of carbon. So there's a lot of carbon tied up in this, and most developed nations are looking at gas hydrates as a possible resource for obvious reasons. You can hold it in your hands and you can light it and it will burn. And your hand is cold, but it's actually subliming methane, so you can light the methane. So it's kind of swamp gas. The geophysical distribution, the geophysics instruments. Now, here's something else I want to show you because this is pretty exciting. This is ASHES, the ASHES vent field, and here is a photo mosaic of the seafloor done by Mitch Ayland, who is the guy who puts on his survival suit so fast. He does not work in it, but he can put it on anytime he wants. And so we have a camera now in this location that will be taking pictures of these kinds of structures. Now, this thing is about 6 meters tall at the topmost, and that chimney grows pretty fast and sometimes gets knocked down by earthquakes. But the rest of it is pretty solid. There is the camera that's on the seafloor, and it is the camera is focused to the right of the, it looks like it's an arrow pointing away, but in fact the camera is focused toward the structure on the right, which is called mushroom. And this is the kind of imagery that camera can take. And you can watch this as much as you want and as long as you want. The little pebble-like things are about the size of my little fingernail. That's what you're looking at. And the hot water is coming out of a vent off to the right and is flowing to the left. You can see that the palm worms with the plumes are also being wafted to the left. And now we're backing away, and you can see the context. 2 berms on the right, 2 berms on the left, black smokers in the middle. We can do this anytime we want. Now, shifting to the caldera itself, where I was just showing you is where the 0.81 meter is, that's Ash's vent field. But measurements have been made of the rate of inflation of the floor of the caldera. When volcanoes are getting ready to erupt, they begin to swell up because there's molten magma coming in from below. And that's actually what's happening. So up where it says 1.2 meters, that's the measurement that's been made since 2011 to 2013. And the estimate is it's 61 centimeters a year is what it's rising. So the floor of the caldera is rising this much every year in that location. Over by Ashes, by where the 0.81 is, it's 40 centimeters a year. Over by what we call the International District, which is close to the 0.57, it's about 28 centimeters a year. Why is this interesting? These measurements had to be made every summer when we would go out. And this is what has been done with those measurements. It's really pretty cool. There was an eruption where the seafloor dropped almost 3 meters in 1998. And then it built up again. And in 2011, it dropped again when it erupted. Both of those vertical lines represent eruptions of magma on the seafloor and deflation of the floor of the caldera. And here's what's going on now. And you'll notice the kink in the cable, or in the yellow line, it increases in slope, and it turns out now it's rising much, much faster than it has been for the last decade and a half. And the implication is when it gets up to about that level, it's going to erupt. We don't know exactly if that's true, but it's a hypothesis. The estimate is it's going to erupt within the next year or so. Why am I excited? Well, when the eruption took place in 2011, nobody knew it happened. And the only way they found out was 3 months later, they were out looking for the anchor to this mooring, and they found the anchor was buried, as was the electronic, or the acoustic release mechanism, was buried in a lava flow. And that is when the chief scientist said, I bet there's been an eruption. And the rest of us all said, yep. But it was 3 months after the fact. Now then, I want to show you circles, red circles. I'm filling them in, see them up in the middle of the caldera and down near the International District. And there's another red circle. That's a tilt meter and a bottom pressure sensor. It has one of Jerry Paros's bottom pressure sensors in it. Jerry is here about 3 rows back and has been a wonderful supporter of almost all of the things that we've done. The bright red rings are where this type of instrument is actually on the seafloor in the caldera, and it's sending back data every minute. So now, unlike having to go out every summer and see what happened, or now, every minute of every day, as Jesse Turner said in his little video clip, we're getting information about the inflation. And here's what the data looks like. The blue line and the red line are tilt. So when the seafloor does this, rises, you can determine the amount of tilt that's involved in which way the tilt is going. And there's an X and Y part to the upper left-hand corner there, and it shows you that there is significant increase in the tilt at particular points. And we know also that these changes, the step function there, is attended by high temperatures in the hydrothermal vents right nearby. So suddenly, it's like we've wired an astronaut in outer space, except the astronaut is a volcano and is 4,000 kilometers away from shore, and we are able to track what's going on. With the cameras, we're going to be able to track what happens to the biological communities. With the water sampling devices, we're going to be able to take water that comes out of the vents when the event takes place or before. Suddenly, we're in a position, because of these people, to actually track what goes on in an underwater volcano. And there are many other parts of the system. It's not just about volcanoes. I'll tell you about the subduction zone where the magnitude 9 earthquake is. We have instruments there as well. I'm just telling this story because for some reason volcanoes turned me on. These are the folks that, the top line folks there, the top folks on the top line. Deb Kelly is the head on the left. The one on the right is something that is made out of styrofoam, and the students often take them to sea and shrink them. The fellow next to Debbie is Mike Mulvihill, and he is the project manager, the program manager, who has seen that this whole program has worked for the last 4.5, 5 years. The fellow next to him, between him and Nancy Penrose, who's on the far right, is Mark Stormer. Mark Stormer is responsible for all the graphics that you have seen in every one of my talks. Nancy is the lady who actually edits the videos from the lengthy conversations that stream out of this Irishman, and they turn it into something that's fairly respectable. All the other folks are critical. I mentioned Oris Pkalka, who's just below Mark Stormer. Cecile Durand, I mentioned before. A number of others here. Mitch is in just below Cecile, who is second from the left. And I won't take you through all the others. Brian Ittig is on the far right on the second line. The engineers, step forward, take a bow. An amazing group of people. These are the ones that delivered all summer long and leading up to all summer long. Some of them were at sea with us, some of them were on shore building things, some of them were testing things, some of them were writing software. I have mentioned a number of them. Gary Harkins on the far left is the director. Mike Harrington and Chuck McGuire are his lieutenants, so to speak. And the HD camera was put together by Ben, who's right next to Chuck. Ben is of the cluster on the top line on the far right is Ben, Patrick Waite, and Eric Bogat. I won't read all the names out to you, but another person who is here is, you see the guy with the jet black beard and no glasses? Just below him, that's Andy Stewart. Just below him with the gray beard and the high intellectual forehead is Eric McCrae. He will be here for you to chat with if you like. He was the one that designed and was responsible for the success of that shallow profiler.
So they're the guys that made all this stuff work.
They make it, this was it. The scientists and the engineers worked seamlessly together to make this whole thing work. It was just unbelievable. And thank God for the students who helped keep track of everything that we did while we were at sea. So what is this about? We can connect the ocean in general, volcanoes, big earthquakes, big storms, major currents, whale migration patterns, anything you want. Fish stock assessment can be hardwired ashore and made available both to policymakers, to educators, to scientists, to the entire human community. And we will learn more and more about how to use this. But I'm telling you, now it actually works. When I gave my 4th lecture, it was a dream. It is no longer a dream. And it isn't yet a nightmare. The future, very quickly. This is something put together by Mark Stormer's son, and I just want to show you this, and I have to stop it to explain a few things. These gray images are seismic profiles through axial seamount. So what you see as outlined in red are cross-sections of a magma chamber. Molten rock has been imaged below the surface wherever there's red, all right? So these are going to be slipped into this 3-dimensional diagram. And then we're going to rotate around, take a look at it. And then we're going to, when we get around to the corner, you can see the grid of the magma chamber down below. We color the magma chamber in. We can even color the parts of the magma chamber that have mostly molten material and the portions that have mostly crystals plus magma. You can see it there. The reddish part, the most red part, is melt only, and mush is in the yellow. Now watch. Here's what happens when an eruption takes place. The magma chamber leaks to the surface. It comes out that crack on the volcano where the caldera wall is, and the magma flows out onto the surface, and this is exactly what happened. This is precisely the pattern of the 2011 magma flow. This is something put together by Mark Stormer's son, Nick Stormer. The mapping of this lava flow was done by our colleagues at the Monterey Bay Aquarium Research Institute, Dave Caress and David Clegg. So we have used sources from many places to put this whole thing together. Now, what's going to happen? When the volcano gets to a certain point, it's going to burst, and the magma is going to come out. And what's that going to look like? Up in the water column, there's going to be a plume that comes out, very hot water that mixes quickly with cold water, but it's going to retain its unique character because it's going to have particles in it, it's going to have microbes in it, it's going to have a lot of heat in it, and it will be uniquely different from the surrounding water. So we'll be able to use these vehicles that you can see cavorting in the plume. There's one down below there, and there's one up in the upper plume.
And they can survive the heat.
They can survive. It's not very hot by the time they're working the upper part. It's only a few tenths of a degree above ambient. But they are designed to map out the characteristics. Some of these were used, these kinds of systems were used to map out the Macondo oil spill in the Gulf. So we know we can do this. Now, again, Mark's son has a fascination with capturing the imagination of a poor country geologist like myself and turning it into something that people can understand. This is what we think a seafloor lava flow would look like, and the vehicle would come in and photograph it eventually and map it as it's happening. We will have the ability to do these things within 5 years. Whales. We're not exactly there yet, but we have the ability to begin tracking whale calls from the large baleen whales to the deep diving odontocetes because we can tell the frequencies and we can tell their distance because we have ranging capability. And many of you have seen whales using bubble plumes themselves to corral their food. Now, what kind of educational program could come out of this? Well, again, Mark and I were brainstorming about it, and all the stuff on the left, and you saw a student-produced video, we can show real-time visualizations, we can show science illustrations, engineering studies, live cruise feeds. That's all input to understanding an underwater volcano anywhere on the planet, but especially here now. And on the right is all the output. It can go to smartphone apps, it can go to electronic books, it can go to video archive, library kiosks, web blogs, theaters. This would be just dynamite. And the heart and soul of it is we can get the real-time data flowing in real time, and we can have educators and researchers and policy folks all clustered around this and taking something out of it that will benefit all of us. This kind of thing could be brought into classrooms all over the planet. It's going to be hardwired to the internet. Now, I said I'd come back, and this is for you, Jerry. We think that something like this, now that we've proven that the fiber optic cable actually works and we're getting lots of data back from lots of instruments in real time, to put in something like this that will allow us to anticipate a magnitude 9 earthquake on the subduction zone, which extends from the Mendocino fracture zone, which is in lower right, all the way up to the north end of Vancouver Island. Our Canadian colleagues want to work with us to do this. I can't imagine that the USGS and NOAA wouldn't find it fascinating. I think the Department of Defense and Homeland Security would be interested. This would be an absolute disaster when a magnitude 9 earthquake hits somewhere in here. We're on the threshold of having the capability not to predict it, but to recognize it very early on with tens of seconds to as much as a couple hours of lead time. In that time, you can turn off electricity, you can turn off gas, and the Japanese are set up to do this. So this is not out of the realm of possibility. Furthermore, something like this would be an unbelievable research laboratory, natural research laboratory, for anybody around the Pacific Rim who's interested in how magnitude 9 earthquakes might nucleate and grow in real time. This would be very, very powerful. I estimate that this would cost, round numbers, $1 billion. Well, what did I say the cost of a magnitude 9 was? Tens of billions. Every single one has cost tens and tens of billions of dollars, and has changed the life cycle of many folks when it happens. Kills many. Ocean acidification, another possibility. We have the ability, we are actually measuring the pressure of CO2 in the ocean, the concentration of CO2 as a gas, and the pH. And those are the two things that are necessary to pin down what's going on with ocean acidification. If we multiply this the same way we want to multiply the seismometers at the base of the slope, suddenly we're in a position to begin to map out the encroachment of ocean acidification and maybe begin to understand the process. This is pretty exciting. Furthermore, if we have these real-time displays, which is what you see here at the Pacific Science Center, that's Alison Fundus with the brown hair on the left, right next to the young girl in a red shirt. And she is teaching just a group of folks down there at Pacific Science Center. Behind the gentleman is one of the big rocks that we brought back from the seafloor when we captured that. We set a trap and captured a rock. Next generation education, what will it be like? You may or may not be using books all the time. You may or may not even be using computers. You may be using something like Science on a Sphere, but in a different fashion. You can ask questions, you can reprogram the thing, you can begin to look in detail at what's going on. There's a lot of potential here, just around the corner, if we have the data flow to support it. And that is what education is liable to look like next generation. This is what our neighborhood looks like. No place on the planet is as well configured as the Northeast Pacific that you're looking at right now for completely comprehensive studies of the edge of the biggest ocean on the planet, the Pacific. And many of the processes that operate offshore, both tectonic as well as oceanographic, are replicated around the world in different locations. So what we're doing here isn't just for here. It has applications in many different locations around the planet. And I believe it will have applications off-planet. I showed this briefly, but the Hubble telescope picks up what they think were 200-kilometer tall water plumes coming out of Europa. When we go there, when our grandchildren go there, they're going to take some of the things that have been developed by perhaps some of the students here in the audience to go to space with them, to go under the ice and begin to explore. We're laying the groundwork not just for tomorrow, but for tomorrow and tomorrow and tomorrow. Now, I'll end also for my good and dear colleague, Veronique Robigoux. This is especially for you, Veronique. We worked together for years, and she taught my son how to speak French. So, this is a piece from The Moldau by Smetana. This was put together by Hunter Hathaway, who also works with Mark Stormer. He mixed the imagery and the music. If you haven't listened to the Moldau lately, do it. So I'd like to end with something from T.S. Eliot, who was a great poet, and from the Four Quartets, it's from Burnt Norton. And it speaks to that almost imponderable concept that we we are both framed by and by which we frame the world around us. It's called time. Time present and time past are both perhaps present in time future, and time future contained in time past. If all time is eternally present, all time is unredeemable. What might have been is an abstraction, remaining a perpetual possibility only in a world of speculation. What might have been and what has been point to one end, which is always present. Footfalls echo in the memory. Down the passage which we have not taken towards the door we have not opened, my words echo thus in your mind. My view is we're dealing with oceans on this planet and hopefully on others, and we want to be guided by the past but not limited by the past, because we're attempting to envision a future that will not be like the past. And that is what we're involved in here. The cable in place offshore gives many, many, many people, especially young folks, the ability to use as much imagination as they want, because what we're giving them is an offshore laboratory with electrical power and bandwidth. They are hardwired to the internet, and they have all the power they want offshore. All they have to do is invent and imagine and create and build and fail and succeed and fail and succeed. And that is the way you learn. And that is what education is about. Thank you very much.